You're live.
Okay, welcome period 7 and the world. We are going to quickly prove the rational root theorem. Are you ready?
Yeah.
First, some number theory background.
Let me get my app.
So, some number theory background. Okay, so there's this symbol. There's this division. No, I'll teach you that later. Okay, so. What is this? Doesn't make any sense. This is a bad way to start the video. Alright, okay, here we go. So, theorem 1. Theorem 1. If A and B are relatively prime, do you guys know what that means? Two numbers are relatively prime. It doesn't mean that they necessarily are prime. It means that they have no factors in common. You guys should just teach that first. A and B are relatively prime. A and B are relatively prime if they have no factors in common. So, for example, like, 15 and 14 are relatively prime. Even though neither of them is prime, but as 15 is 5 times 3 and 14 is 7 times 2, they're relatively prime. Cool? Okay. So that's like a thing. Alright, so theorem 1. Theorem 1 says, if A and B are relatively prime, so they have no factors in common, and if A and C are relatively prime, then I can conclude that A and BC are relatively prime. If you think about that, it just makes complete sense. Right? Yeah. A and B have no factors in common, and also A and C have no factors in common, then of course A will not have any factors in common with B times C. Because what is B times C? It's just all the factors of B times all the factors of C. Is that good enough of a proof for you guys?
Yeah.
Alright, I'm happy with that. Okay, alright, theorem 2. If A and B are relatively prime, then A is also relatively prime with any power of B. This also makes complete sense, right? If A and B have no factors in common, then A is not going to have any factors in common with just like a whole bunch of B's all multiplied by each other. Can I get vigorous head nods if you're cool? Okay. In fact, theorem 2 is just an application of theorem 1, where like C is just another B and then like a bunch of them. Okay, here comes the cool one. Theorem 3. If A and B are relatively prime, and A divides BC. Did y'all teach this symbol last year? Sounds like a no. When we write A divides B, how do you pronounce this? A divides B. This is just a way of saying A goes into B, or B is a multiple of A. So this just means that B is the form like A times K, for some natural number K, or integer, I guess probably I should do. Cool. So A divides B, A goes into B, B is a multiple of A, however you want to say it. Okay. So if A and B are relatively prime, and A divides BC, so what can I say? Gabe, conclusion? If A and B have no factors in common, but A goes evenly into the product of B and C, I think you're saying it backwards, but yeah, then A is a factor of C. Yup. Then A must divide C, right? Just think about it. If A goes into this product, but A and B have no factors in common, then B must not be helping at all with the fact that A goes into C. This is just okay. So I don't know. Do you want a little example of this one? Like we'll take these two right here, right? 15. So example for just this third one. 15 and 14 are relatively prime, yeah?
Yeah.
And suppose A what do I want to do? So suppose 15 goes evenly into, well, this is a little bit hard. I have to like multiply both out, right?
13.
No, wait, 13. No, but it doesn't. It goes into 14 times like 3. No, but it doesn't. I have to take the what am I doing? 30?
Yes.
Multiply 14 by
No,
something.
but
Multiply 14 by 15.
sure. Or let's just do like, no, but I want,
Oh, 420.
this is like my A and this is like
Do
my
420. 420.
B. Yeah, okay, good. So if 15 goes into 420, then what is 420? Is that
420 is 14 times 30. So
14 times 30? Yeah, okay. So yeah, so 420 is 15 times 14 times 2, like that? Is that true?
yeah.
30, yeah. Okay, so if 15 goes into this number 420, which is after all, 15 divides 14 times 30, then the 14 part of 420 is not helping me get into 420 at all, right? It's only the 30 part. So my conclusion from this is that
15 divides 30.
15 divides 30. Okay, thank you, Rancho. All right, good. All right, these are 3 facts of number theory. If you like this kind of stuff, there's a whole class called discrete math where we look at these things more carefully. And I didn't really prove them, I just kind of talked them out. All right, so why are we doing all of this? Back up here. We're going to prove the rational root theorem. All right, so here comes the rational root theorem. And I think it's actually maybe good to sort of restate what it is we're trying to prove. Or at least, maybe we'll do that kind of as we go. All right, so here is here's like a hard math proof. It's not obvious at all what to do, and it sounds kind of complicated and sort of really obvious. And you guys may have observed over your life that there's like this inverse relationship between how obvious something is and how hard it is to prove sometimes, right? Like it's really obvious that it ends up being kind of hard to prove. Okay, and it's a very like low-level thing, and it's going to involve rational numbers and whatever like that. That being said, 90% of this proof is just writing out very carefully all the definitions of all the things involved, and then there's just like one moment when you have to do like one tiny little smart thing. Okay, so this is really more of an exercise in like how to be kind of a mathematician. Most of it is just writing things out very carefully, and then you have to do just a little bit of thinking. All right. Okay, rational root theorem. Let's be smart. What does the rational root theorem say? There it is up there. It says, if p is a polynomial with integer coefficients, blah, 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 blah. So, where do we begin? Step 1. It's the very first thing that we should do.
What's in this matrix?
It's not hard. The very first thing we should do.
Write out the polynomial.
Write out what polynomial?
Just like ax times.
Yeah, Kevin says start with just like a polynomial, right? Like an arbitrary polynomial. Yeah. And it has to have integer coefficients. Okay, table over here in the corner, off camera. Brilliant. They say, hey, if your theorem is about any polynomial with integer coefficients, I guess we should just start with a polynomial with integer coefficients. Brilliant. That's how you do math. If someone says prove something about all triangles, what's the first thing you do?
Make
You
a
just
triangle.
take a triangle and then you just kind of start. Okay, good. Excellent suggestion. So, the first step, already pretty easy. Let p of x be a polynomial with integer coefficients. Alright, now it turns out that this is actually a little bit hard because Kevin, why is it kind of hard? You recommended saying something, but then you kind of stopped talking after about the word 5.
X.
What were you about to say? He said like A,
X.
X, and then he just stopped. Why did he stop?
Because he doesn't know what degree.
Yeah,
it should
Mindy.
be.
know what power.
Because he doesn't know what degree it is, right? Is that why you stopped? Yeah, so this is like annoying, right? Because we have to do it like in general. So we want this to be true for all polynomials of arbitrary degree. What that means is advanced notation is required. Okay, so we're going to write this out. We're going to say that p of x is an nth degree polynomial. Because it has to be of some degree, so we're going to let it be of degree n. And if it's of degree n, then the first term is going to be x to the n, and the leading coefficient will be like a sub n, like so. Okay, and this is my notational convention. A sub n is just the coefficient of an nth of the leading term. Okay, and then the next one is like a to the n minus 1, x to the n minus 1. And then like, et cetera, et cetera. You guys okay with this? Okay. What's the second to last term of this polynomial following this notation? A sub 1x. Yeah, it's the second to last term will have degree 1, so we call it a sub 1. And then the last term, a sub 0. Okay, good job. And now, so that's like a general polynomial. And now we have to add in a couple of, we have to explain ourselves a little bit, because after all, what is intended here? Integer coefficient. So I better like note off to the side that all of these numbers are indeed integers. So a sub I is an integer. This is the fancy math way of doing this. Just noting that you're introducing a thing, you're introducing a bunch of numbers, they're all integers. And there's one or two little more small things I need to mention. This is kind of a little tricky and technical, but very important. Alice. What can't be 0? Okay, Alice is worried about like constants or something like that, right? Is that what you're worried about? Yeah. You're sort of on the right track, yeah.
N has to be an integer.
N has to be an integer. Okay, yeah, that kind of goes without saying, but alright, sure. Sure, I'll add that, yeah. So N is, in fact, it better be like a positive integer. So we can do like that. Okay, yeah, but I wasn't even going to mention that because we take that for granted, but okay. Wait, there's another problem. I'll give you a hint. Is this really an nth degree polynomial? We want it to be an nth degree polynomial. So there's a little bit of a technical point, but we should mention, like, is this term really here? Or are we just like faking? Yeah. Yeah, let's just say that it isn't. Right? So yeah, so let's just also insist. I mean, we're the ones starting the proof, right? So we're saying, look, this is an nth degree polynomial. So if it's really an nth degree polynomial, then don't try any tricks with me here, right? Like that leading coefficient can't be 0. Otherwise, like, you know, use a different n or whatever. Okay, and then there's one more trick. What else would be sort of like silly? Yeah, because after all, so can you say that again louder?
A is 0 can't be 0.
Yeah, we don't want this to be 0 either, because like, does anyone have an explanation for that? I mean,
You just factor
well,
out.
like, yeah, this whole theorem is about the numerator of the root being a factor of the constant term. If there's no constant term, then this whole thing is just stupid. By the way, why can't I just ignore polynomials without constant terms? I mean, if you just give me some polynomial with no constant term, why is that kind of like, why do I need to just like not care about that at all? You know, you just pull, Alice is like, dude, you just pull the x out. After all, the whole point of the rational root theorem is it helps us find roots. And so, if there's no constant term, I can just pull out an x, and then I can just focus my attention on what's left over. Is everyone cool on that? Okay, so we only really care about polynomials with constant terms, because other things can just be dealt with other ways. Okay, good. All right, it's getting very technical. Also, we haven't done anything yet. We just wrote a polynomial on the board. Okay, next. Suppose that, oh, what's the next step? I forgot. Let's just let you do it. What's the next part of this theorem? If p is a polynomial with integer coefficients.
Create some arbitrary roots.
Someone else besides Alice.
Lick it.
Or Alice. Lick it. What?
Yeah, lick it.
Alice.
No, I don't know.
Oh, she doesn't
I was
know.
gonna say like A0 together, but
Oh, she like starts stuff. No wait, the very next sentence of the theorem is if p has a rational root. So,
Plug in arbitrary rational.
or just suppose that it has a rational root, right? So suppose that p has a rational root. Suppose p has a rational root. In other words, what we're supposing is a couple things. We're supposing that p of like c over d is 0. And, so this is like kind of in brackets. And we need to be, since we're doing a real proof here, we should write everything all out. What am I supposing about this c over d?
C and D are integers.
Same stuff as before, but a little tiny extra twist. Thanks, so just tell me what to write.
C and D are integers.
C and D are integers. That's just simply what I mean by rational. D can't be 0, thank you, Mindy. And,
Lowest term.
yeah, but now we can be a little bit cooler. Instead of saying lowest terms, what does it really mean if a fraction is in lowest terms? Yeah, another way of saying a fraction is in lowest terms, the big boy way of saying that is that C and D are relatively prime. C and D are relatively prime. They have no factors in common. If they did, then you could divide. Okay, so far we got it, polynomial with integer coefficients. So far we supposed that this had a rational root. We still haven't done anything yet. What is it that we're actually trying to prove?
That the root, that there exists.
What am I supposed to prove? What does the rational root theorem actually say?
That D is a factor of leading coefficient.
D is a factor of the leading coefficient. In other words, D should go into A sub n. So, yeah, we can again use kind of like, big kid language. What we need to prove is that this rational root that I'm supposing exists, that the denominator of that rational root divides, A sub n, sorry. That the denominator divides the leading coefficient and C, the numerator, is a factor of, in other words, divides A sub 0. Okay, good. All right. Now that we've done all that, aka we haven't really done anything at all, we can start the proof. Okay. So here's what I know. I know I have a polynomial. I know I have integer coefficients. I know if I plug in C over D, I get 0. And I know I need to prove this weird fact about the divisibility. Okay. First step. Use what you know. We don't know that much. Only like one really big
Very nice.
that we have.
You know, C over D.
Yeah, I know that C over D is a root. So if I know that C is a D over a root, what can I do with that?
X minus C over D.
Just
Divide.
plug it in, man. He's just like, dude, plug it in. Of course that's what we're going to do. Yeah. Plug in C over D. And if I plug in C over D, I'm going to get, all right, this is kind of annoying. Don't cry. Don't be scared. It's going to be all right. We just have to do all this crap, right? This is going to be A sub n C over D, like to the n, plus A sub n minus 1 C over D to the n minus 1. You guys with me? You guys, it's not so hard, actually. Just plugging crap in. And if you do that, plus A sub 0, we're going to get 0. Okay, so yeah, we're just using the fact that we know that's a root. Well, that's nice, because now I have an equation. All right, what can I do with this equation? There's one more way I can make this equation way happier. The joke is getting old 5 years ago. All right, what can I do to clean things up considerably? This is a small, no, we're still not at the one, you have to do, the one good thing you have to do is coming later. But we still have to do, what can we do to make this is kind of ugly. Why is this ugly?
Fractions.
Fractions. Fractions are terrible.
Multiply everything by D to the n.
Yeah, this guy gets it. What can we do to get rid of all fractions?
I just said it though.
Multiply by
0.
something on both sides which will make everything have no fractions anymore. What is that number?
D to the n.
D to the n. Okay, everyone do it. Multiply both sides by d to the n. Yeah. Don't be scared off by the notation and subscripts and stuff. It's pretty chill, right? If I multiply this guy by d to the n, the denominator's gone. If I multiply this one by d to the n, I have one d left over. Yeah? Did I mess up? Over here, I should get a sub, that should be a 1, right? A sub 1 times, that d's gone, and I have n minus 1 d's left over. This is just exponent rules, and then here we get this. Okay, good. Alright. So far, I would call this like trivial. As in, like, we haven't really done anything that requires any kind of insight or anything like that. We just kind of like did stuff. What's beautiful about this equation is all the a sub n's, all the a sub i's are integers. C is an integer. D is an integer. So this equation has a very beautiful simplicity to it in the sense that it is absolutely nothing but sums and products of integers. Okay, right, so now I don't need to worry about fractions. All I have is just a whole bunch of numbers being multiplied and added together. All right, so I'm going to give you guys a minute. Can you think of one, can you think of one cool thing we have to do now? Actually, there's two things. Let's just like look, this one just has some C's in it, no D's. This one has C's and D's, C's and D's. This one has just a D. Well, wait, did I screw up again?
No.
Why does this look all weird?
Does it? I don't know. Oh, I think, no, actually that's right.
Everything's fine, right?
Yeah,
Yeah,
yeah.
these notes are just wrong. Stop looking at those. Good. Yeah, so do you want a hint?
Sure.
Okay. Move this term over to the other side. And I'm actually going to split this up. You probably didn't pay your paper for this, but oh well. I'm going to split this up into two different equations. And in the first case, I'm going to move this thing over to the other side. Okay, so I have a to the n, c to the n, plus a n minus 1, c to the n plus d, plus a sub 1, c d to the n minus 1, equals negative a sub 0 d to the n. Okay. So again, all I did was I moved that one term over to the other side. Well, now I can do something cool. Oh, by the way, what was my goal? Maybe we should be like keeping the goal in mind, right? I need to prove this and I need to prove this. People at home, do you know? We have to do one thing.
What? Divide?
Yeah, but better than dividing.
Multiply by?
Yeah, factor out a c. Every term on this left-hand side has a c in it. Okay, so factor it out. So if I factor out a c, okay, more annoying exponent algebra going on. Carl, don't fall asleep. Good. Factor out a c.
Yep.
Carl, what do you get? Read it off to me.
You get a sub n c to the n minus 1 plus a sub n minus 1 c to the n minus 2
Whoa.
d.
Good. Yeah, keep going.
Plus ellipses. Plus a sub 1 c. Wait, no c. A sub 1 to the n minus 1.
Yeah, good. There we go, Carl. Dot. But ellipses, I like that. That was cute. All right, good. Okay, what is the significance of this? Now you should be seeing it. Why is this so great?
I don't know.
Well, I don't need to do any dividing because it's just all number theory. You could divide. I kind of see what you're talking about. But what am I trying to prove? Which of these two can I sort of prove right now? Yeah, this one, right? I need to show that C is a factor of A sub 0. But notice that, remember that C and D are relatively prime. So, wait, do I want to divide by C? No, I think we just look at it and we just say,
Yeah, we can use like that thing.
yeah, we just kind of use that thing over here, right?
Yeah,
So what I have is that, I guess the one I want to use is, wait, hold on, I'm losing track of my business. C, oh, yeah, this whole left side of the equation is a multiple of C, right? Yeah, this is the what you have to say. This whole left side of the equation is a multiple of C. And therefore, this side of the equation also is a multiple of C. Right? I showed that the left-hand side is C times something, so if that whole left-hand side is a multiple of C, then the right-hand side is also a multiple of C. But if that right-hand side is a multiple of C, then C, my conclusion is that C must go evenly into A sub 0 D to the N.
Sure.
Right?
Yeah.
But C and D have no factors in common. If C and D have no factors in common, then C and D to the N also have no factors in common. And then by our theorems up there, if C goes evenly into A sub 0 times something with which it has no factors in common, then conclusion, C divides A sub 0. Well, I'm just kind of blowing off the negative for the moment just because who cares, but yeah. Get it? Okay, how do I do this second? Notice this like weird fork. How do I, so this one's done. How do I prove the other one? If you guys get it, then we should be able to do the second half just the same.
Yeah.
What do we do now? Yeah, not Mars.
Subtract by AN, CN.
Yeah,
A sub
take
n.
the one term that has no D's in it and get it over to the other side. Exactly. So we get A sub n minus 1, C to the n minus 1 D, plus dot dot dot, A sub 1 C D to the n minus 1 plus A sub 0 D to the n. And then on the right hand side I'm going to have negative A sub n C to the n. So I just moved that first term over to the other side, like Mad Mars told me to do. Now what? Class, now what?
Same thing, divide by D.
Factor out a D from the left-hand side. And if I factor out a D from the left-hand side, because they all had D's in them, then I conclude that the whole left-hand side of this is a multiple of D. But if the whole left-hand side is a multiple of D, then the right-hand side is also a multiple of D. And knowing that that right-hand side is a multiple of D lets me conclude that D goes evenly into A sub n C to the n. And again, if D goes into two things, but D and C to the n have no factors in common, if D and C to the n are relatively prime, then the only way for this to be true is if D divides A sub n. And thus I got my second one proved. Cool. I think that's kind of cool. All right. Not sure whether that was worth it. Let's say yes. That is something that like almost no one ever does. All right. The rational root theorem in all of its glory. That was the proof. Should we say goodbye to period 7? Bye, period 7.
Love you.
Bye, Catherine.
Okay.